the additive industry in its entirety is because of 3D Systems. The guy that founded 3D Systems, Chuck Hall, still works for our company. He's 83, 84 years old, still comes to work every single day. He filed the first patent for additive manufacturing, or 3D printing at the time, in 1983.
Welcome to the HPA Tune In podcast. I'm Andre, your host, and in this episode, we're joined by Joe from 3D Systems. 3D Systems is the originator of additive manufacturing, which is what we generally call 3D printing. The founder of 3D Systems, Chuck, back in 1983, was the man who applied for the very first patent relating to 3D printing. Now, this is still a relatively new technology, and that's exciting because it is changing so quickly. In this interview, we talked to Joe about his background in mechanical engineering, how he worked for an OE manufacturer before ending up at 3D Systems. We go into depth about the technology involved with 3D printing or additive manufacturing of both plastics as well as metal. And this actually uncovers some of the assumptions that I had made about the strength and reliability of these particular 3D printed or additive manufactured parts that couldn't have been further from the truth. This is a really interesting dive into this technology and how it is being applied. And while I know we look at this from an automotive and motorsport sense, this is a technology that is being used across a broad range of industries, including, interestingly, healthcare, and we learn about how additive manufacturing is potentially on the verge of being able to be used to actually print or make replacement organs, which absolutely blew my mind. Now, granted, the equipment that 3D Systems is manufacturing is not at the enthusiast level, so I just want to preface this whole interview with the fact that no, you're probably not going to listen to this interview and then rush out and buy a multi-million-dollar metal additive manufacturing machine. However, it's still valuable to understand these technologies, the fact that they exist, the fact that they are moving so quickly, and you can still leverage this technology, not by owning the machines yourself, but instead by utilizing some of the companies that already own this equipment and just farming out your work to be manufactured by them. Before we jump into our chat, for those who are new to the Tune In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to tune EFI, how to construct wiring harnesses. We also cover topics on fabrication, 3D modeling and CAD, race driver education, and data logging, just to name a few. You can find all of our courses at hpacademy.com/courses. All of these courses are delivered in high-definition video modules that you can watch from anywhere in the world, provided you've got an internet connection. This means you can learn from the comfort of your own place and you can learn at your own pace. All of our courses also come with a 60-day, no questions asked, money-back guarantee. So if you purchase them for any reason at all, decide it wasn't quite what you expected, no problem, let us know. We'll give you a full refund. And for podcast listeners, you can also use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. We'll put the coupon code in the show notes to make it nice and easy for you to find. Lastly, if you like free stuff, then I've got a great deal for you. We are constantly partnering with some of the biggest names in the aftermarket performance industry to give away some great prizes. You can always find our latest prize at hpacademy.com/giveaway. It might be an aftermarket ECU or dash. It could be some engine components or engine building tools, or just about anything in between. They are great prizes, and we will ship them free of charge to your door if you're the winner. There's no tricks here, no purchase required to get your name into the draw. All right, enough with our introduction. Let's get into our interview now. All right, welcome to the podcast, Joe. Thanks for joining us today. Your situation here for 3D Systems, which we're going to be talking about, is a little bit unique compared to most of our guests. But anyway, I know you're still passionate about cars, so let's talk about your background and how you formed that passion.
Yeah, absolutely. Thanks for having me on. I grew up just kind of obsessed with cars from a kid, like, sitting on the couch pretending to drive cars when I'm 4 years old, and it just kind of grew and grew from there and tried to get involved in the motorsports and just car industry as much as possible. So kind of went the traditional background of a mechanical engineering degree and tried to pursue anything I could in the automotive industry after that. So that's kind of where it started.
When you were sort of considering what your future was going to look like, you've already mentioned, obviously, passionate about cars from a very young age and wanted to work in that industry. Were you specifically looking at a particular area of the automotive industry that you were passionate about sort of pursuing a job in?
Yeah, I mean, I always wanted to work for an OE. I always wanted to go to work for a General Motors or a Ford or that kind of thing. I grew up in the northeast corner of the United States, kind of near Michigan, but not too close. And you kind of see the development in the cars. Occasionally, you see a prototype out on the road in camouflage and things like that. And that's what really really drew me in is the automotive OE space.
Okay. So the mechanical engineering degree, that's sort of a staple of probably, I'd guess, maybe 50% of our podcast guests. So nothing particularly unusual there. Maybe for those who are absolutely fresh to the podcast and haven't really heard much about what mechanical engineering as a degree entails. Obviously, it is a very broad topic. Can you give us the cliff notes on what your degree actually covered?
That's exactly it. So any mechanical system that's out there, a mechanical engineer designed it. I mean, any product that you can think of, doesn't matter what industry, doesn't matter what it's in, there's an engineer behind it, usually of a mechanical variety. If it's a mechanical device, electronics engineers or electrical engineering focused on electron, same concept. So the general degree is very, very broad. You get your hands on a little bit of everything, really get into the math and the physics of how systems work and things like that. But it is a broad degree and it kind of sets you up to kind of go anywhere out in that platform. It's kind of an interesting story, actually. When I was getting ready to go to college, or as you guys would say, university, I was adamant there was a mechanical degree specifically for the automotive industry, an automotive mechanical engineering degree. That's all I wanted to do. That's all I wanted to go to school for. It was actually kind of interesting. My dad, right before I was getting ready to go, pulled me aside and he goes, if you go into automotive engineering, that's it. You're doing automotive engineering. A mechanical engineer could be an automotive engineer, but an automotive engineer might not be able to be a mechanical engineer somewhere else. As a kid obsessed with cars, I didn't want to hear that, but I want, if anything happens and you need to pivot into some other form of engineering, you've got the broad background to do it. You're not just kind of laser focused on the automotive industry. And that ended up being the route that I went.
Sure. So, I mean, in essence, a mechanical engineer could work in the automotive field like yourself or could design a bridge.
Yep, absolutely. Yeah.
Because it's that broad, and obviously there's significant differences between an automotive product and a bridge, let's be clear, is there a point in that degree where you start to niche down into particular topics that kind of drive your future?
I'd say the degree in general still stays pretty broad. You kind of learn a little bit of everything, fluid systems and thermodynamics and that kind of stuff, as much as dynamic systems and statics, bridges, that kind of thing. You kind of learn a little bit of all of it, and then there's opportunity for you to branch off and kind of specialize beyond that, or take additional courses or focus elsewhere on kind of additional topics. But it generally stays pretty broad.
Okay. Now, maybe for some of our listeners who are at a point in their life where they're looking at what they're going to do at university or college and thinking, hey, maybe a mechanical engineering degree sounds something I might be interested in, but are put off by the fact that maybe they're not that great at maths. I'm going to guess that a mechanical engineering degree is fairly math intensive. Do you have to be a rocket scientist to even take a degree like this, or is it not too challenging?
I'm by no means a rocket scientist, but yeah, it is pretty math heavy. You got to work at it. The math at times, depending on, what area you're in, when you get into some of the thermodynamics and things like that, the math can be complex. I think when you're going through university, going through college, they really drive into, the formulas and the background and the figure it out on a calculator or by hand. It's challenging. It's difficult to do, but if you want to do it, you can work through it. The real answer is once you get out into industry, once you get out into the real world, you're not doing math by hand. There's programs set up, there's FEA, there's all this other stuff where they really drive into learning the fundamentals so you know how and why this stuff works. Then once you get out there, there's tools to do it. You're not doing it by hand anymore or anything like that.
I'm glad you mentioned that, because that was absolutely going to be my next question. How much of the stuff that you're learning are you actually putting into place? But I do absolutely agree, understanding those fundamentals and the principles behind it, going through the hard work of doing it by hand, I think is really important, rather than just relying on a tool. The problem with these tools as well is it does become a bit of a case of garbage in, garbage out. And if you're blindly believing the output, not realizing you've made an error, or maybe there's a problem in the tool itself, that can really set you up for a pretty bad time.
Exactly, 100%. Especially, FEA is pretty prolific in the automotive space from a design standpoint and everywhere else. And the statement of garbage in, garbage out is 100% true. That model and that math in the background is only as accurate as the inputs you're given it. If something's not dead on or not true to size from what the model thinks, that's the result you're going to get out. And, we'll talk into this as we move on, but physical testing is still a thing for a reason. Physical validation testing of parts. The math in the background's only so good. The software writing the algorithms to do the meshing and the FEA and all that is only so good, but it still comes down to physical testing at the end of the day to confirm those results.
Yeah, absolutely. Now, again, we'll elaborate here. You've used that term FEA, and for those who haven't heard that before, we're talking finite element analysis, which is a computerized way of basically modeling the stresses and strains in a part, and essentially working out if it's going to be fit for purpose and strong enough to put up with the forces that it's going to be exposed to. The garbage in, garbage out element there, I've always sort of found, particularly if we're talking about something like maybe a suspension arm or maybe an upright or something like that, the issue I see is understanding what the forces involved are actually going to be, so you can input those correctly into the FEA. Because, for example, the shock load that is going to be input into those parts when we run a curb or something on a racetrack is obviously different than just steady state cornering. So there's a few challenges there, but obviously used properly, FEA is a very, very powerful tool that's going to allow you to design parts that are fit for purpose without being unnecessarily heavy to get that strength. Let's move into your work experience. You said you wanted to work for an OE manufacturer, and that's exactly what you did. Where did you go to, and how did you actually end up getting that job?
Yeah, yep. So once I graduated school, I had a job that I was actually working during college. It started as an internship, turned into a full-time job, which actually gave me great background. It was at a sheet metal shop doing pretty basic sheet metal contracting, stamping, forming, that kind of stuff. But it was a huge learning experience from a background perspective, because again, it's like the mechanical engineering degree. The more you broadly understand processes that make components and parts, the more you can leverage that knowledge as you move forward. So I did that for a little bit, and then got the opportunity to go work for a company called Delphi, or Delphi Technologies, tier one automotive supplier. So, the big OEs, 90% of the components that they bring in to do the final assembly on a car, they're all farmed out to sub-suppliers. So Delphi has been around for years and years and years and done a little bit of everything. They've got an electronic side, they've got chassis, they've got suspension, they've got engine components, they've got evap components. They kind of, any subsystem that gets farmed out anywhere, they did a little bit of it. And I ended up at a spot that is one of their centers of excellence for powertrain development. So really, really unique facility. And I spent my time working on valve train components for the majority of the time that I was there. So in your valve train, there's a system called a cam phaser. It phases the cam. It's a cam phaser, right? So that is the piece of hardware that enables variable valve timing. So pretty standard stuff now. At the time when it first came out, it was kind of oddball, and everybody said that's not going to work type thing. But it's an interesting piece of technology that allows smaller engines to be really fuel efficient and get good fuel economy, good emissions and things like that, but also allows you to make more power than you should be able to in that same configuration by alternating, intake and exhaust valve timing to let the engine breathe a little bit better, but then you can kind of choke it off and get really good emissions when you're not on the throttle trying to make power.
Sure. Yeah, I think continuously variable cam timing these days is kind of almost expected, so nothing particularly unique about it at this point. But that cam phaser, as you mentioned, obviously the key to that system working. I want to dive into that in a bit more detail, but before we do that, I kind of hear from a lot of people that have worked at an OE level that they kind of get stuck working for 3 years of their life on the left rear tail light or the latch mechanism for the passenger's door or something of that nature, something kind of pretty dry and hard to kind of really get excited about. You're smiling though. It sounds like you had a pretty good time. Was that your experience or was it completely different?
That's 100% accurate. I mean, touching on what I said earlier about if it's a product, a mechanical engineer had something to do with it. There's 30,000 parts in a standard OE car. And guess what? There's probably a team of engineers working on every single one of those components. Like you said, 99% of it, not really that glamorous. Internal latching components. I mean, there's people that design clips that hold a wiring loom in place, right? That's nothing sexy or exciting, but it's part of the process.
Yeah, someone's got to do it.
Yeah, exactly. So it depends on what you end up doing and what you like. I mean, being able to get involved with these developments and these development programs on these vehicles years and years and years before anybody even knows this vehicle is going to be a real thing, to me was still exciting. Even though cam phaser is a cam phaser, not terribly exciting, but knowing what the end product was that it was going into, having input to these kind of things, and some of the cam phasers I worked on in production setting, there was an intake cam phaser and exhaust cam phaser. Each one of those was a little over 1 million parts a year for sustained production. And to say, oh, I can point to any one of these cars and say, guess what? That's got the cam phaser in it that I designed. Sure, it's a boring part, but to me, it's still exciting.
Oh, and there's definitely a claim to fame. I'm interested, sort of, with that cam phaser part, is this something that was solely you working on it from sort of the original concept through to the final production part, or is this again a team effort where you've got 20 or 30 Joes all working to make this one cam phaser?
Sure. I'd say usually in the automotive industry, it's always teams. You've got guys with a huge amount of experience, huge amount of background, leveraging those people. And then it's always kind of a checks and balances type thing is that, I could come out and design the greatest thing ever. And somebody could come in and say, well, that's not going to work. And here's why, right? Having that teamwork, that community to go through and, work through designs, work through things like that. And there's a story I always joke around and I tell from my time when I was at Delphi, that I'm always blown away and amazed that vehicles for sale are as cheap as they are, which everything's crazy expensive now. It's kind of a joke, but working on a tolerance stack, right, to make sure our stack up of components is going to be exactly right. We had 3 engineers in a conference room on a whiteboard for a half an hour, only talking about one radius on one washer. And this was no joke. It was straight tolerance stack, soup to nuts, make sure everything's right. And 3 of us spent a half an hour all radius, one feature on one part, just to make sure in a production setting, it's always going to fit. It's always going to go together. It's always going to do its purpose. You're not going to have any wear, things like that. And utilizing a team to do that, right? There's no way anybody can get into the weeds on all this stuff and get it dead right every single time without, having a team of people working on it as well.
No, for sure. That term you've just used, tolerance stacking, can you just clarify for our listeners what you actually mean? Because I think that's something that probably most people would not consider.
Yeah, sure. Absolutely. So in an assembly, right, even a simple assembly, let's say you've got 4 or 5 parts that fit together and they're just stacking vertically on top of each other. The overall height of that stack is determined by adding each piece up, right, to make its overall height. Well, if each one of those is 1 centimeter tall and they stack up and the whole assembly is 5 centimeters tall, that's your perfect condition. That's what it's supposed to be. That's nominal. That's what it's designed as. In the real world, you're never going to machine or print or cast whatever a part that's 1.0000000, right? There's always some level of tolerance. There's always some level of variation. And when you have a stack of 5 parts and each part has a variation, you need to understand how big that variation could be and how far that total assembly height, that stack of 5 pieces, can vary end to end. 5 cubes stacked on top of each other. Super simplistic example. When you've got radial components stacking up with linear components and things like that, and then you've got, look at a crankshaft with each one of the connecting rods on it, right? All of that all stacks up and all of that has to locate pistons in the right location and things like that. They get really, really complex, but in order to guarantee that everything's going to fit and work as designed, you've got to know that everything, even with all its variation in production methods and things like that, will still land in a zone where it will still work. So that's kind of concept of a tolerance stack.
I guess the other aspect with this as well is with each of the individual components with its own tolerance. Maybe it's a centimetre plus or minus 0.1 of a millimetre, just for an example. The tighter you want that tolerance, the closer you want that to the exact dimension, the more expensive the finished part's going to be.
Yeah, absolutely. Getting, when you get into really, really, really tight tolerances, you start even talking about surface finish. If your surface finish is too rough, that'll push your part out of tolerance, things like that. Or, a flat surface is a flat surface, but when you have a really tight tolerance and you zoom in really far, nothing's perfectly flat. And you start to take that into account and things like that. And then when you're talking from the OE realm where I came, if you can make one part that's perfect right on tolerance, great, nobody cares because we've got to make 1 million of them a year, right? And your production methods vary, machines wear, tools wear, things like that, and you've got to work all the way back to all of that to make sure you have a robust process that can handle all that variation.
Sure. All right, so how did you sort of transition out of this enthralling cam phaser task into working at 3D Systems?
Yeah, so I actually spent a little bit of time at the tail end of my time at Delphi. Got moved over into their evaporative emissions portion of their company. So super not exciting. Talk about door latches and things like that. For people that aren't familiar, next to your gas tank in pretty much any modern vehicle since the 70s, you have an evaporative emissions canister. Us gearheads, us performance people, take that thing out and throw it in the trash, right? But it's actually kind of interesting what it does from an emission standpoint, but it's also recycling fuel. So basically it's a box with activated carbon in it. I always joke it's charcoal, but activated carbon soaks up fuel vapor that would normally leave your gas tank and go out into the atmosphere. And instead, OEs, they'll capture that and then kind of push it back to your engine. So you're using that. And kind of interesting fact is on average, they say that saves the average user about 20 gallons of fuel a year that would otherwise just evaporate out. It's a huge number. And then you multiply that across every car on the road, it makes a huge difference. And then that fuel vapor gets pushed back to the engine, normally just to do fuel trim and things like that. It's not really driving the car forward, but fine trim and stuff like that, they'll use that fuel vapor for. So those boxes, those enclosures, they're all designed specific to the chassis, specific to the vehicle, specific to the engine size, the gas tank size, a lot of requirements that go into it. And it really boils down to every single one on every single make and model of car is different. It's not a standard piece that, here's your Chevy truck that's the same on every Chevy truck. Well, what engine is it? What's the gas tank size? That kind of thing. They proliferate a lot. So when we were in development, we would print them. They're traditionally, when they're in their final form, fully, production in a vehicle, there's still a nylon material, a nylon box, basically. Nylon's one of the materials that prints great for additive manufacturing. So we had a nylon SLS, selective laser sintering printer in-house, conveniently made by 3D Systems, that we would make our prototypes on, do our development and things like that. And the thing that made us really productive and really unique in the market is because of this printer and its ability to print nylon, which was the end material, in a condition that was almost as robust as the final injection molded piece. We could go from blank sheet design to, here you go, here's your final design of a canister. Go bolt it in one of your mule vehicles and test it. Not theoretical, not anything else. Here's the physical part. Go out and test it. We could do that in a couple weeks' time. From blank sketch, here's your minimal requirements, here is the packaging envelope that you have to work with, and we could turn around in a few weeks flat and say, here's a functional part, go bolt it in your vehicle and test it, go run it, go drive it around. You can do all that.
So that speed of prototyping is really one of the keys, which we're going to get much deeper into with additive manufacturing. So you kind of obviously saw the benefits from firsthand use of that machine.
Yep, had firsthand experience with it and immediately saw the benefits. And like I said, we'll talk to it more, but this was only in a prototyping stage. And, to see the ability to turn something around that quick that was a functional part for a limited amount of time to go do some testing and things like that, saw what it could do, saw the capability of it. And then as I moved on past my time at Delphi, I ended up in a location where 3D Systems existed. So I'm in our Denver, Colorado facility, one of our centers of excellence globally, where we're doing development on components, materials, printers, all that kind of thing, and just kind of enthralled with the technology and what it's capable of doing, and ended up here doing that.
Okay. All right, well, let's get a little bit of a quick sort of 30,000 foot view of what 3D Systems is. So give us a sense of, location or locations and, how many staff are employed by 3D Systems.
Sure. 3D Systems is a global company servicing pretty much every market, every area on the planet. Globally, we've got almost 3,000 employees. We've got sites and centers and development, things like that all over, globally all over. We've got sites specifically focused on plastics throughout the US and Europe. We've got a couple sites focused specifically on metals in Europe and again in the US. And then kind of the main thing is we're a company producing printers. We want to sell printers, get users manufacturing parts on our printers. That's kind of what I always say is I just want to see parts being made additively. I don't care how you do it or how you go about it. I just want to see more additive parts out in the industry. And we have got kind of all that soup to nuts from a service perspective, things like that globally. Your guys' neck of the woods, we've got a bunch of customers down in New Zealand. We've got a company that I would definitely tell everybody to go check out, Rodent Cars, has a bunch of our printers, both on the metal side and the plastic side, doing really, really cool work over there. Guys are super smart, making really, really unique parts, and they're pushing the limit of what the technology can do and what you can do with a part made with that technology is really cool to see.
Right. I think probably this is a pretty good place to sort of preface this discussion for our listeners that the products, the printers that 3D Systems are producing, these are commercial level, professional level products. So these are not at the enthusiast level, correct? And we will talk a little bit about pricing as we go.
Yep. Yeah, absolutely. So the kind of more on the, and we'll get into this. So spoiler alert, I'll break the news now. These are set up to be industrial pieces of equipment, manufacturing parts. Not, you can do prototyping, and I've used them in my past, and we still use them to this day for prototyping, but they're set up to run serial production, run all day long, 24/7 type thing in an industrial setting, manufacturing parts. We'll talk into this in later, but prototyping versus production with additive manufacturing, kind of a dead argument at this point. Real production parts come out of additive machines all day long, all over the globe.
Great. I mean, again, we will get further into this, but one of the I think expectations people have with this manufacturing technique is that it is only useful for a rapid prototyping style of manufacture as opposed to a finished part. So we'll park that and put a pin in it for the moment and come back to it. In terms of your actual tasks within 3D Systems, what are you actually doing day to day?
Yeah, so I'm an applications engineer, pretty focused on the metal printing side of things, but I kind of get my hands on a little bit of everything. But basically, my role within 3D Systems is help customers develop applications, develop components for additive manufacturing. So we do that kind of all over the place on all different levels. We work with customers that, their whole product portfolio is made additively. They know additive in and out, and we help do the final development and put things like that into production, all the way down to customers of, I didn't even know you could print parts in metal type thing, and developing their component or their part to do what it needs to do in its final environment. So kind of a little bit of a Swiss Army knife that I'm involved in kind of all of our industries. My passion is in the automotive industry and motorsports, but I spend a ton of time in our healthcare space. Healthcare is latched on to additive really, really early on, especially on the metal side when it was still kind of in its infancy. The healthcare space took advantage of it because it fit a sweet spot of it could produce a part that you couldn't make any other way that had significant performance improvements. And not to say cost doesn't matter, but in the healthcare industry, right, cost is kind of if it does its job, people will pay for it type thing.
Yeah, cost kind of secondary.
Yeah, exactly. And then we do tons of work in the aerospace realm. The semiconductor industry has gotten really big lately. Oil and gas, anywhere where you can design a component that's got a step above in performance, kind of helping out with that. And to touch on 3D Systems in general, kind of where we started here, crazy piece of information that I always like to give out to people is that the additive industry in its entirety is because of 3D Systems, specifically our founder, Chuck Hall. So the guy that founded 3D Systems, Chuck Hall, still works for our company. He's 83, 84 years old, still comes to work every single day. He filed the first patent for additive manufacturing or 3D printing at the time in 1983.
Wow, that is definitely a claim to fame.
He invented the entire industry, and it's all grown from that one idea. He was actually embossing business cards using a photopolymer to put a raised logo on a business card. And why can't I do this on top of it over and over again and make a three-dimensional part? Made it work in his garage with some photopolymers and actually printed an eye wash cup, just as an example of, hey, I made this cup out of layers over and over again. Filed the first patent for it in 1983, started this company in 1986, and anything tangentially related to additive manufacturing came from our founder and that one idea, which is pretty wild. So the whole kind of industry had proliferated from there.
I feel like at this point, maybe he deserves some time off. Maybe he could even retire. I don't know.
Well, people have been telling him that for years. He loves it though. So we'll get a little tangential here, and then we'll get back to on topic. But he's off in like sci-fi land right now. We have a portion of our company that he's now dedicated his time and research to, specifically for bioprinting. So with the goal of we're going to print organs, replacement organs for human, and they're actually shockingly far along in the process in making it work. They've got lab scale small organs. They're focused specifically on a lung right now. That is working in a functional lab-based setting right now with the goal of animal and human testing in the very, very near future. And then there's another part of that that's specifically basically the term that they kind of use as a cell on a chip. So you can have an organism on basically a microchip like a computer, and you can do drug and virus testing and things like that without needing a host animal or a human to do that testing on. You can do it in a lab setting and print a functional organ, a functional cell that you can target specifically with drugs, therapy, things like that, to now rapidly increase the time from, we think we have, vaccines. Everybody talks about vaccines now. We can rapidly decrease the time to testing a vaccine to put it into market, because we can do a substantial amount of testing in a lab on a 3D printed organ to figure out if it works or not. What positives and negatives, there's always the side effects of drugs and things. Like they can figure a significant portion of that out ahead of time in a lab before furthering the process. Or maybe they say, there's too much risk here, it doesn't work, we can kill this idea altogether without having to spend huge amounts of money, huge amounts of time, and kind of expediting all that, which is pretty wild.
That is truly mind-blowing, and gives some insight into what the next 5 or 10 years might end up looking like in the healthcare arena. Now, obviously, our main focus and interest is automotive and motorsports, and 3D or additive manufacturing is pretty well known and established in that area. But it is great that you've just sort of shown how broadly this technology can be used across multiple industries. And I think most people would probably have a sense of that, but 3D printing organs, I wouldn't have guessed that was anywhere on the horizon. So interesting. All right. Let's move on and actually start talking about what this term additive manufacturing, most people call it 3D printing. What's the term actually mean?
Yeah, so it's pretty literal, the term for it. You're manufacturing a part, a component, a what have you, additively. You're adding material over and over and over again to that component to make your final component. Where traditional manufacturing are now kind of termed subtractive manufacturing, right? If you think from a machining standpoint, you start with a big block and you you subtract material over and over and over again until you end up at your final part. So kind of two schools of thought. You start with a big piece of material and you end with a smaller component, or you start with really, really small material and you end with your final component by adding to it. So pretty literal term for it, but that's it.
This process, I assume, also is significantly more efficient in its use of material if we compare that to CNC machining of a piece of aluminium billet, for example. Obviously, depending on the specific product you're making, you might end up removing 80 or even 90% of that original piece of billet, and that kind of becomes scrap. Yep, sure, you can recycle it and get cents on the dollar, but additive manufacturing, you are only putting material where that material is necessary.
Yep, exactly. So there's a bunch of different types of technologies when it comes to additive, different ways of doing the additive process. But on the whole, yeah, you're applying the material to the part where you want it and where you need it, and nothing else really. So the rest of that material doesn't get used, and it's ready to be used to print the next part, make the next feature, things like that. Kind of our our joke that we say all the time is, lightweighting or adding complexity to a part is free. And you guys can't see me, but I'm putting this in quotes over here. Free because you're using less material to make a really lightweight part, where normally that's exactly more tool time, more CNC time, more chips, and it makes a more expensive part. Lightweighting a part with additive makes a more efficient and cheaper part, which is kind of school of thought that you really got to wrap your head around. But adding really complex features, internal geometries, things like that would be crazy expensive or otherwise impossible with some of these other technologies, you can do it cost effectively and easily with additive, which is makes it unique tool in the toolbox, which is kind of another thing that I always say, right? Everybody comes in and, oh my God, additive is going to take over everything and everything's going to be printed and you'll never do anything. Not the case. It's a tool in the toolbox. You're always going to cast parts. You're always going to injection mold parts. You're always going to machine parts, but you're also going to print parts, and it's going to have its place where it's got its strong suits and its weak points, and it's good for some applications and it's not for others. It's another tool in the toolbox that it will get out into the industry more and more and more and become more relevant.
Probably getting a little ahead of ourselves, but it seems you've just mentioned this. You sort of already talked about manufacturing using additive manufacturing technology for a production run. I'm assuming here that this is going to be well suited to, first of all, prototyping, but then small production runs of parts. And the example that sort of straight away pops into my mind is Koenigsegg, which they're well known for using additive manufacturing for a range of parts on their cars. But of course, they're not producing 100,000 cars a year. I assume at some point, just it becomes commercially non-viable to 3D print parts versus casting or other traditional manufacturing technologies.
Yeah, absolutely. And we've got some pretty interesting ways of calculating that, where you can create a curve of, here's my initial investment and here's how many parts I need to get out to, make this rate of production, and the same curve with additive. And there's always an intersection point, and it depends on the part, it depends on the size, it depends on the complexity. It could be, printing 2 parts is cost effective, but if you go to print a third, you could have done it some other way. And it's really easy to explain in the plastics sense, that an additive plastic part versus an injection molded plastic part, that additive plastic part, even if it's same size, same weight, same material, same function, it's going to be significantly more expensive. But you can do the math to calculate backwards of, if this additive part is, just making up numbers here, if this additive part is $100 a piece and the injection molded part is $5 a piece, there's a huge delta there. But to get to that injection molded part, you've got to spend $200,000 on a mold. So you can calculate that backwards to say, hey, if I only need 10,000 of these things, it's still cheaper at $100 a piece to do them additively than invest in the mold and then make the parts really, really cheaply. Now, that's always a sliding scale. If it's 1 million parts, that math swings towards, okay, spend the money on the mold, injection molded. But there is always an intersection between those two paths of, is additive cost effective to that point?
I guess as well as the cost, we also need to consider that additive manufacturing is going to be, well, at least I assume, I might be wrong here, a slower process of producing these parts than the likes of injection molding, like you've just talked about.
Yeah, that's a great example. Injection molding, been around since forever, in the 50s, highly optimized, high throughput, great accuracy, things like that. Plastic additive, or additive in general, usually, if you put it at the 30,000 foot level, is a little bit slower, and there's things you can do to optimize that. So building batches of parts at once, printing as many parts in your build volume as you can really drive efficiency up and drive piece price down. But at the end of the day, you're still adding material one by one to each individual part on a pretty micro level, versus an injection mold, right? You're cramming plastic in as quick as you can, let it freeze off, and on to the next part. So,
all right, let's start by talking about what most enthusiasts would be familiar with, which is 3D printing of plastic materials. But there's still different technologies involved with the way this can be done. And I mean, the usual enthusiast level products, which we have in our workshop, the likes of, we've got a Creality and a Bamboo 3D printer, and they use filament, which is heated up and essentially laid down on a base platform. What do 3D systems do? How do your printers work?
Yeah, so the technology you're referring to with those printers there is FDM. So you're extruding a filament, and kind of normally it's on some sort of gantry, if for lack of a better term, moving the print head around and laying down layer by layer. I'd say the same way I said additive has this place where casting and machining works. Every single one of the additive technologies has this niche where this is the technology that it's suited for. So the FDM style printers, usually they're pretty cost effective, and they can produce parts quickly, and you can get your hands on parts quickly, cheaply, easily. Kind of the helpful point there is the ease of access to that technology. And then you branch out from there. 3D systems, like I mentioned earlier, kind of founded on the idea of SLA, or stereolithography, and this is scanning a vat of resin, liquid polymer, and curing it, photo curing it with a laser to create your part. So it's a much smaller. If you think of your print head on your printer there, it might be making a bead of plastic that's half a millimeter or a millimeter wide. With the laser, you're now curing a line of plastic that might be 100 microns wide, or a tenth of that, right? So speed might not be as quick, but your fidelity goes way up. And then you have the ability to manipulate speed and power and things like that to do different things with either throughput or material properties, or that kind of thing. And then you can branch off into SLS, or selective laser sintering. Similar process, but now we're using a powdered plastic as opposed to a liquid plastic. And there's pros and cons there. That the powdered style, due to the way that it's done in a heated chamber where everything's kind of homogeneous and held at a relatively simple or stable pressure to its surroundings, is those parts print without supports. There are no supports in an SLS style process. Your material properties are really, really good. You're printing, nylon, for example, that's got almost identical properties to a regular piece of nylon, things like that. And then there's multi-jet printing, where you're using a binder and jetting the material down that you want, which allows you to do all sorts of interesting things. We use it heavily in the jewelry industry, weirdly enough, where you can print highly detailed wax castings out of wax directly, and then you can go turn those into your mold. And we could talk about this a little bit later, but additive manufacturing doesn't always have to be you print your final part. You can print an intermediate step for a casting, for example, where you can leverage the throughput and the speed of additive manufacturing, but then you still go make your part the traditional way. You're still going to go cast it, things like that. So there's different technologies for the different uses and the different materials. Sometimes, one material will work well for one technology and not for another. So they all kind of subdivide and have their space specifically on the material and the application you're using it for.
Okay, so much more complicated than I would have thought on face value. So great to know. Am I right in assuming that the SLA method, one of the key advantages over the consumer level products that we've just discussed, is the accuracy that you can print the finished part to?
Yeah, the accuracy, the materials that are available are different. The material properties you can do are pretty significantly different. I know we'll talk to it in a little bit. With FDM, you're extruding a layer on top of a layer on top of a layer, and left and right of those layers, they're all kind of tied together and they have good mechanical properties. But vertically in between those layers, they're only kind of slightly adhered to each other. So maybe your mechanical properties in that axes aren't as good. Where some of the other plastics technologies, you get more of an isotropic effect on your material properties, where the height pulling in the height versus pulling left to right, there's no real difference. Where FDM, that might not be the case.
Okay, so a stronger finished product.
Yep, stronger finished product, better material properties, and then resolution. The layer thickness that you can print in a traditional extrusion style printer might be large, and that might be good because you can print a part very quickly, or that might be bad because you can't get the resolution that you want out of it. So having the ability with some of these other technologies to print very, very thin layer thicknesses now get into a part where you at times can't even identify that it's made with additive manufacturing. And then you can do kind of black magic in the background with texturings and things like that. I always use the example of your dashboard in your car. It's not just a smooth piece of plastic, because anything that ever happened to it, you'd scratch it, you'd look at it and it's scratched, you bump into it and they apply that texture, that noise pattern to it to hide defects. Well, in some of these fine featured plastic additive side, we can use that noise, we can use that texture to actually hide the layer lines to the point where you get an end use part that you can't, unless you've got a really, really trained eye, you can't tell that it wasn't injection molded, for example, because there's no witness, there's no layer lines. It's difficult to see the level that was finished at.
As I think that's one of the sort of giveaways we expect now with the extrusion style of 3D printing. It's got a very clear and obvious surface finish to it, and it's not smooth. So obviously that technology, as you've just mentioned, completely different, and you're going to get a way smoother surface finish, which we'll talk a little bit at the end about some of the case studies for this, but a lot of companies such as Sauber and Alpine Formula One teams are actually using your 3D printers to actually do aero testing. And straight away when I read that on your website, I was sort of thinking to myself, well, I've seen the surface finish of some 3D printed parts, and I don't know how well that's going to really work out for aero testing. But obviously that now sort of the pennies dropped, it all starting to fall into place.
Yeah, exactly. So 3D Systems in general has had a very, very long relationship with F1. This company has been around since the mid 80s and heavily involved in Formula One, into the 90s and throughout today, heavily in many, many of the teams in many, many different areas. My love-hate relationship with Formula One, from our perspective, is if they utilize this technology and do some of the coolest things you have ever seen with it, and I can't tell you guys publicly about it, which is the biggest bummer because there's so many components, so many parts where it's just incredible what they're doing with this technology. And Formula One, everything's, NDA'd out the wazoo, and any edge that you get in performance, you want to hide it under wraps so nobody else can see it. But the utilization of that there, so this material that we're talking about is our accurate composite. It's a PIV material, so it's set up specifically for particle imagery velocitrometry. I can never say the word right. Basically, wind tunnel testing. So they have particles going through the wind tunnel that they can pick up with cameras and lasers and things like that to see the airflow at a really, really high resolution. So 3D Systems developed a material that is extremely hard, extremely rigid, so it can stand up to that wind tunnel testing, that force. The caveat is there's always a trade-off. It's brittle. It's a very brittle material. It's made for short run. Try it out, test it out, but it's not a durable material. But it is extremely stiff. It's got great feature fidelity. It's great at holding its shape. It's also, if you go and look at our website, you can find it or see some of the case studies. It's like sear your eyes out neon purple, and that's explicitly so you can see the particles moving across it in a wind tunnel. So they took that into account ahead of time to make the kind of output of the wind tunnel, which is the measurement and the movement of those particles, as visible as possible. So the material is used in huge amounts in Formula One and some other industries. That, talking with and working with these teams, I'm sure you guys on this podcast have talked about CFD or computational fluid dynamics before, similar to an FEA, except now we're looking at fluid flow. They use that technology, the digital version of a wind tunnel, in a huge amount to iterate super quick, to find, the best solution to this area. But when they're ready to go put that on the car, this is to our garbage in, garbage out conversation earlier. That input and that output is only as good as the information that went into it and the math behind it. And they still want to see those results proven in real life before they commit to, all right, now we're going to do layup of, 100 of these front wings or something like that before they spend the time and the money on the tooling and the investment there. So they'll physically print the part that they think is the right answer, and they'll go run it in the wind tunnel. And with the speed of this technology and the accuracy of this material, they've got the ability to iterate. You could do a wing design or a winglet or a dive plane or something like that, and you could try it out in the wind tunnel and then try it out in the wind tunnel 3 more times that day with 3 different designs, where normally, you either couldn't test it or you had somebody laying these parts up by hand, and you're talking weeks or months of development, where now you can iterate in real life multiple times within the same day.
Yeah, I think the part with that, particularly at Formula One, obviously time is so critical for the development of these cars. And also they're now operating under budget caps as well. So they have to be a little bit smarter with how they use their resources. The CFD that you mentioned, obviously a quicker and much cheaper way of at least finding the general design trends that they want to go down and experiment with before they actually commit to manufacturing parts and then wind tunnel testing. But as you mentioned there, really needs to be validated in the real world, in the wind tunnel. And an interesting anecdote, I bring up Adrian Newey's book probably just about every second podcast. And, basically what I'm saying here is if you haven't read it, go and get a copy. It's absolutely amazing. But he talks about a story from his earlier years. I think it was the Williams, actually, that Ayrton Senna died in, and they were having massive trouble because they'd transitioned from the active suspension FW15, I think it was, don't quote me, and the whole aero package was optimized for that particular active suspension platform, and they struggled with adapting to going back to passive suspension, and everything sort of worked really well. I'm hoping I'm talking about the right car, but anyway, the explanation will still be relevant. Everything worked perfectly in the wind tunnel, and it was giving all the numbers that they expected, and everyone was happy. But the reality was that the car was super unstable when it actually was out on the track. And Adrian, I think, worked out that basically the airflow under the car was stalling, and that was making it unstable. And they ended up working out, and as I'm explaining the story, I'm pretty sure I'm talking about the wrong car, but anyway, as I say, this is still relevant. They found that the moving ground plane in their wind tunnel, there was an oak panel underneath it with holes perforated so that the moving ground plane didn't actually get sucked up to the underside of the car due to the low pressure area. And that oak platform actually had a big bow in it, so it was no longer flat. And that was sort of driving him in a direction of making this more and more aggressive underfloor that in the real world just was stalling. So good example there of, the wind tunnel is a great tool, but even there, that's still just a tool, and it's what the car does in the real world that's important. Obviously, they found that problem with the ground plane, and modern wind tunnels probably don't have that issue, but just a nice little anecdote there that I thought I'd chuck in for free.
Yeah. Absolutely.
I just wanted to take a moment out of our interview with Joe and talk about a course that's super relevant to today's topic, and that, of course, is our 3D modeling in CAD for Motorsport course. Normally valued at $199 US, you can use the coupon code 3D50 to get $50 off, bringing it down to just $149 US. And I know that this is a technology or a skill set that can be so beneficial to enthusiasts at home building their own project cars. It's not that difficult to learn, particularly when you go through the process presented by Connor in this course. You'll learn the basics of CAD, what CAD is and what software is available. You'll learn about the design fundamentals, essentially how to design a part that's fit for purpose, something that's going to be strong and reliable, which is obviously super critical. You'll learn about solid modeling basics, 2D sketching and 3D sketching. You'll learn about extrudes and holes, revolves, sweeps and piping, etc. You'll also learn about the basics of sheet metal modeling, which in my opinion is one of the really powerful uses for software like Fusion. You'll then learn about assemblies, the basics of assemblies, as well as joints and constraints. You'll learn about analysis and analysis tools. You'll then learn about post-processing, including part drawing views. You'll learn about dimensions and tolerances, exploded views for assemblies and drawings, just to name a few. We then move into advanced CAD, such as surface modeling, simulation and finite element analysis, generative design and automated modeling. We also cover 3D scanning and printing, and we finally finish the course off with a 5-step CAD design process. And this is a simple 5-step process that you can apply to designing your own part, irrespective of what it is and irrespective of what software you're using. We also include a library of worked examples within this course, and this is an informal walkthrough of that 5-step process just to really cement all of the information shown within the course. We add to this library of worked examples from time to time as well, so this course will continue to grow with you. So again, that course $199, usually use the coupon code 3D50, that'll bring it down to just $149 US. We still have options to break that payment down at checkout. You can break it down into as many as 8 individual weekly payments to make it as affordable as we can. Remember, Irrespective of how you purchase though, you are still protected by our 60-day no questions asked money back guarantee. So if you purchase and for any reason at all decide that the course wasn't quite what you expected, let us know. We'll give you a full refund of the purchase price. All right, so in terms of the materials that you can print in plastic or with a plastic printer, can you give us sort of a quick rundown on some of the more common materials and kind of the strengths and or pros and cons of those?
Yeah, so I would say one of the biggest developments in maybe the last 5 or 10 years from the plastic additive standpoint is really the materials. The technologies and the machines we're using to print them with are always evolving. They're getting bigger, faster, stronger, more efficient, things like that. But the biggest real step change I would say in recent time with from a plastic standpoint is the actual material properties and the actual material that we're printing, ever getting closer and closer to this has got the exact same properties as an injection molded part, for example, right? That's the goal, is get it to a point where you're now printing parts that have identical material properties to a traditionally manufactured part. So that's kind of the biggest development, I would say. And if you go look at 3D Systems website, they've got a smattering of a little bit of everything. So materials that are very similar and act the same as an ABS material or a polypropylene. Nylon, I keep mentioning, is a big one just because out of the printer, very, very similar to a nylon part, and it can go straight into service, into use, however you want. And then you've got low durometer materials, things that are rubber as well, things like that. The ability to produce highly rigid, high temp materials that we've actually got a couple materials that are flame retardant. So we do a ton of work in the aerospace industry where they've got specific requirements on flame retardancy for, aircraft and things like that, where this material, if in event of a failure somewhere else in the plane, this material can't then go and catch fire. It's got to be flame retardant. It's got to be flame proof. So doing things like that. And then you get into the composites. We'll talk to that a little bit later. Composites, things like that. Like I said earlier, the healthcare industry is really grasp a hold of additive manufacturing. So biocompatible materials that either can contact your body or go in your body that don't irritate or things like that. From the metal standpoint, right? Titanium, there's no reactivity with your body in titanium. So titanium's used everywhere in the healthcare industry as a contacting material, things like that.
And what I'm kind of picking up from this is anything and everything goes here.
It's trying to cover as many bases as possible, and it's always growing and growing. Yeah.
Okay. Before we move to metal printing, I'm just interested, you mentioned composites, and carbon filaments are a material that can be 3D printed. And I've sort of always wondered with that material, we know the properties of carbon fiber are pretty impressive, but how does a 3D printed carbon part hold up or stack up against a traditionally molded part? And my question here is, with the mold, we've got our carbon weave and we've got control over the direction of the filament, the weave, and it's also, most importantly, I guess, continuous across the molded part. Whereas, the additive manufacturing technology, we don't have that continuous filament, or at least that would be my expectation. Am I right or wrong here? And if I am right, how does the strength stack up to a traditionally molded part?
Yeah, absolutely. There's a bunch of different layers, and customers and people on developing parts always hate me when I come in and say, well, it depends. It depends. It's too many different layers, too many moving pieces. But if you look at what we were talking about with the extrusion style printers, where it's extruding a constant stream of material and that's got a continuous fiber in it, that can have really good material properties around the part because it's one continuous fiber and it is joined the whole way across. But when you shift layer to layer, you put tension layer to layer, you don't have that continuous fiber going through those layers. So there is, again, what I touched on, non-isotropic properties to that material where you pull left and right and it's got great properties. It's got that carbon fiber in there. When you pull up and down, there's nothing going through those layers, transitioning layer to layer. And you have material properties that suffer there. Then if you look at the powdered plastic style printing, the SLS style printing, they have, glass filled and carbon filled materials there where it's diced up, either glass fill or carbon fill, kind of balances the two where it's not the same properties that you're used to, but now it can handle load and tension in different directions. But then, there's the kind of third piece of this is figuring out ways to cheat it or get around that problem that you have between layers and things like that. And then that's, the design of your part, and then also the orientation that you build your part in. So orientation of building your part is a huge portion of additive, regardless of what technology you're talking about. So if you're developing a part that you want to print that's carbon fiber impregnated or has a continuous fiber in it, and that part's only going to see load in one direction, well, you can print it in a direction where it can handle that load, and that's not a problem. You don't have the trade-off of those layers and things like that. So skinning the cat layer by layer, there's always many, many facets that go into it. And I'd say on a high level, yeah, not the mechanical properties you know and love out of carbon fiber, but you can design around that or use the properties to your advantage to get around that.
Yeah, well, it sounds like at minimum, definitely not the downsides that I had in built up in my head. And really interesting how you mentioned, just designing the part to be printed with the orientation of the expected forces in mind. Interested, what is the sort of steps between, we've got our 3D model, our CAD model in, Fusion or maybe SolidWorks or whatever our favorite go-to 3D modeling software is. How do we sort of go from that model to being able to print? Is it just as simple as Control P? Or is there sort of a software step in between, like we'd see with CNC machining, where we've got a CAM software to actually create toolpaths, etc.?
Yeah, there's still that intermediate step. So you're taking whatever your 3D model is, however you generated it in today's day and age with the software that we have. Pretty much doesn't matter how you modeled it or where you modeled it from. You can get it in a state where a 3D printing program could accept that 3D model, whether it's an STL, which is kind of the native file type for 3D printing, or especially with us on the metal side, we're just using native CAD files now. The software can figure that out. If you modeled it in SolidWorks, it'll open it up and it'll still be the same parameterized model that you designed it in, or SolidWorks or NX or any of those type of programs. But kind of taking it from your modeling software and putting it into the printing software is how we figure out the orientation that we're going to print it in. Depending on the technology, it might need supports. It might not need supports.
Just for those who are not up to speed with it, talk about these supports, because this is quite a common aspect with 3D printing. What are they and why are they required?
Yeah, absolutely. So when you're building it apart in additive, again, depending on the technology, as that part builds up layer by layer, if you have geometries that, let's say you're printing a hole in the middle of your part, when you go up layer by layer, at some point the top of that hole is going to start closing and reconnecting to itself layer by layer as you build up. And again, depending on the technology, if there isn't anything holding up the top side of that hole, when you start printing over air effectively, right, it has nothing to build on top of it. It'll just kind of crumble in on itself. So at a high level, most of the additive technologies need supports to locate the part, to hold it in place, and then we'll go down the rabbit hole of metal additive, which is its own ball of wax, but those supports have a third function in there as well.
Sure. So this requirement for the support, I mean, we see this with the extrusion style, but you still require this with SLS and SLA printing technology?
SLS is the unique one where you do not require support. So SLS, basically, I kind of touched on it earlier, but the whole powder bed that you're building within is held at pretty much a constant temperature. So that whole chamber heats up to 5 to 10 degrees C below the melting point of the powder. So it's all right at a stage where it's about to melt and turn into one big solid block. And then we use a laser to just tip it over that melting point and create a solid part. Because everything is held at one continuous temperature pretty much the whole way through the process, there's no stress, there's no thermal load, there's nothing else put inside the parts, and they're all kind of just hold themselves in place and do what they're supposed to do. So when they come out of that process, they don't really move around or deflect or need to transfer heat elsewhere or locate themselves because the powder bed moves. So SLS is kind of unique that your final part, pretty much as printing, comes out of the machine. There's some additional processing to the part itself, but that's kind of a unique spot where you don't need supports. Pretty much every other style printing, those have to locate features and hold them in place as the part builds up or as the platform moves while it's building.
All right, so talking about SLA, for example, where the supports are required, the software that you're talking about, does that kind of automate the process of building in these support structures, or is that still something that is, you actually have to do manually?
Yeah, from the plastic side, it's now gotten to a point where it is mostly automated. There's always pros and cons. There's always, experience where, hey, I've printed this part 100 times and I know that if I put a support here, it's going to cause problems, or if I put one here. And there usually is some level of engineering touch to make sure the supports are doing what you want it to do. From the metal side, different ball of wax. Supports are pretty complicated. They're still pretty manual operation. The software will automate a bunch of it. It'll guide you through a bunch of it. But at the end of the day, making sure it's done right and is going to do what the supports need to do is still a bit of a manual process.
Sure. All right. So, in terms of the plastic printing machines that you offer, obviously there's a range and they come in different shapes and sizes. But just for interest's sake, could you ballpark us? What are we talking here? Are you sort of in the sort of $50,000 to $100,000 vicinity, or are we sort of out the stratosphere?
Yeah, sure. So huge range of printers, huge range of technologies. If I was to bookend it, we've got a smaller SLA style printer. It actually uses a projector instead of a laser. So you cure layer by layer in its entirety. It builds really, really fast. With a small print volume, we use it for building fixturing and tooling and things to hold parts all day long. Great, great printer for that. That starts in the $25,000 USD range. And then you blow out the other end of that spectrum. And I mean, we've got plastic printers that can print parts that are 1.5 meters long, 0.5 meters wide, and 0.5 meters tall. And yeah, you're into seven figures when you're looking at printers like that, and kind of everything in between.
Yeah, okay. As you'd kind of expect. Just actually touching on the size of the printed part, obviously that becomes a limitation. And as you've just alluded to, the bigger you want to print, the more money the machine's going to cost. Kind of, don't have to be a rocket scientist to figure that out. However, at least with the enthusiast level equipment that I've been exposed to, there are still solutions of, breaking a part up into multiple components and printing it that way, so you can actually end up with a finished printed part that's bigger than your printer can do in one go. I assume that that's still the case for your equipment as well.
Yeah, absolutely. And like you said, there's multiple ways different to do it. Most softwares built in have nice features to add tongues and grooves and things like that, where you can clip parts together afterwards. Depending on the material and the print technology, you'd be surprised how well super glue works to put huge assemblies together. It gets the job done and it works great. And kind of anything in between there. So chunking up your part, building it in pieces and assembling it is still definitely a way to get the job done.
Yeah, okay. All right, I think we've probably covered plastic, so let's move on to the other part here, which is additive manufacturing using metals, 3D printing of metals. Can you, again, give us a bit of a rundown on the basis for this technology, how it actually works?
Yeah, we're speaking my language now. I always joke I'm a metalhead, metaphorically and at work. I'm our metals guy. So metal printing, which when I started at 3D Systems, wasn't totally familiar as a technology. And I'm sure, the mass audience and things like that are new to metal additive. But you can print functional end-use metal parts using 3D printing. So it's very similar to the SLS style of printing, powdered style of printing that I talked about earlier. If you want to get into the weeds, the overarching technology is called laser powder bed fusion. There is a laser and a bed of powder, and you're scanning that bed of powder with a laser to create a part. That's the overarching technology that makes the metal printing that we do work. So very, very finely ground metal powder scanned in 2D with a laser, and then you put down a really thin layer of metal powder again, scan it with 2D with a laser, and build your part up layer by layer after that. So the powder is finer than powder sugar. It's really, really unique to see that actually, if you put all this powder in a bowl and move the bowl back and forth, it flows like water. It's that small of a particle size, which just creates better accuracy and better surface finish in your parts.
What sort of metals can be printed in this method, using this method?
Yeah, sure. It's same as the plastics, ever growing. There's tons of engineers working on that day in, day out. But we've got a little bit of everything. You've got kind of plain tool steels, kind of, plain carbon steels. We can print stainless steel. We can print, coppers. You can print Inconel, aerospace grade, super nickel alloys, things like that. Titanium. I always leave things out. Aluminum. Tons of grades of aluminum, things like that.
Okay. So basically, just like the plastics, there's really nothing you can't print.
Yep, exactly.
All right. Is it a wasteful process? I mean, obviously, we're additive manufacturing, which we've already talked about, so maybe less wasteful than machining from a block of billet. But am I right in assuming that this powder is completely reusable?
Yeah, so especially on our systems is a little bit unique as the powder from a technical standpoint can't say completely reusable, but it's extremely close. The reusability of the powder is based on, some of the material properties that the powder creates. Technically, it's got a lifespan. Technically, it's got an end of use. We always say you'll turn the powder into parts before you ever run into that scenario. But yeah, you're only using the material that you're using to physically create a part. When you take that part out, all of the rest of that powder is recycled, goes back into the machine, and goes into printing the next part. So I touched on it a little bit earlier that producing a lighter weight part or a thinner, leaner part actually creates a cheaper part, and all the powder, all the material you didn't use to make that part goes right back into the machine and prints the next part.
Yeah, fair. In terms of the cost of the materials, and obviously this is going to depend on the specific metal that we choose to print, but I mean, if you compared aluminium, for example, the cost of X kilograms of billet versus the same kilograms of this powder that you can then additive manufacture your parts from, how do they sort of stack up cost-wise?
Sure. So you kind of lose it on the front end, but you gain it on the back end with the material recyclability. But the powder itself is not cheap. There's no way to beat around the bush. The powder is expensive. So basically, the powder is taken from a piece of billet and turned into powder. So you've got your regular billet that you could use to machine. Well, now it needs to be turned into a powder form before you can print it. So that process traditionally done, if you want to get into the weeds, a process called gas atomization, where you're basically feeding a piece of billet or a piece of bar stock basically through a plasma spray to melt it, break it off into tiny little droplets, and then re-solidify it as powder. So it's a pretty intensive process, and it's not cheap. So you're taking the same billet you would print with anyways, and now you're turning it back into a powder, so then you can turn it back into your final part. So it is significantly more expensive, but then the recyclability of it kind of outweighs that.
Yeah, no, that makes sense. Obviously, in terms of print time or manufacture time, it's going to totally depend on the size and shape and complexity of the part that you're printing. But could you give us an idea of metal printing versus maybe plastic printing? Are they one and the same in terms of speed of print?
Yeah, a little bit different. Metal printing at a high level does take a little bit longer. Basically, the amount of energy density or the amount of heat you have to put in the material to solidify it again is much higher with metal. And so usually that means the process moves a little bit slower. And then there's different ways, to skin that cat with more lasers or thicker layer thicknesses to increase that productivity. There's ways to get around it. But like you said, it really depends on the part itself. Printing big, chunky, blocky parts is kind of inefficient because you're building it with a laser that's scanning back and forth, really small laser spot size to then go backwards and make a big chunk of metal. So that adds a lot of time to the build, things like that. So when you're building thin, lean parts, you're not utilizing that much material. It builds fairly quickly. So, on the scale, small little metal parts you can build in a couple hours. We've built some parts on our biggest 3D printer, which can print a 0.5 meter cubes. You can print huge, huge parts, heavily used in the aerospace industry. We've run builds that take 12, 14 days to print, start to finish, to make a single part or maybe two parts, things like that. Falls anywhere on that spectrum.
Sure. Now, I'm not a metallurgist, but on face value, again, I'd sort of consider, much like the conversation around the plastic printing, that these finished 3D metal printed parts are going to suffer from an inferior grain structure compared to a piece of billet or maybe a forged component, whatever you may be dealing with. Any truth to this, or am I just completely off track here?
Yeah, so the metal additive in the scheme of all additive technologies, are all 3D printing is relatively new. This technology start to finish is, 12, if you want to average out time, 12, 14 years old, or even the plastic printing is, been around since the 80s and developed from there. So the technology is kind of new. So when it's infancy, 5-10 years ago, you were completely right. The technology was still evolving. The material wasn't fully dense. Issues with grain structure and things like that were still being worked on, still being solved. In the state that it's in today, I mean, titanium is one of the materials we print the most of, kind of our bread and butter. That material out of the machine is 99.98% dense compared to a piece of billet. So you're 0.02% off on density. It's right there. And then from the grain structure and things like that, also not a metallurgist, but I know enough about it to be dangerous. There's processing that you can do to that material afterwards to get it in line with what you're trying to do, mostly from a heat treatment standpoint. You can use different heat treatments to manipulate that grain or that grain structure, or target mechanical properties out of the material. You can manipulate hardness, you can manipulate things like that to really hone in on the material properties. And it's not much different from blacksmiths making a sword. They go and quench that at the end to get material properties out of it. Still the same thing. You're going to manufacture the part, and then you're going to perform a heat treatment or something else to get the material properties you want. Same thing in machining. Machine parts still get heat treatments afterwards to target material properties. You can do the same thing here.
Yeah, okay. That's actually completely reasonable when you think about it. Yeah, you don't just machine a part from billet and then necessarily it goes on the car. There are often some post-processing operations that are required. From an automotive and motorsport sense, what do you kind of feel lends itself ideally to additive manufacturing using metal technology?
Yeah, sure. This is actually a great kind of indicator for additive in general, but specifically the automotive industry. The kind of phrase that we use all the time is high mix, low volume. So when you're making a lot of different parts, a lot of different components, things like that, but you're not making a lot of them, that really narrows into the sweet spot of metal additive or additive in general. So we talk Formula One, and we'll talk more about Formula One, right? They've got to make a certain number of cars, certain number of components, and it needs to be the absolute optimal performance, bar none. Sure, there's budget caps, but cost doesn't matter. Things like that doesn't matter. Just make the most optimal performing part you can, and we're only going to need 10 of them, 5 of them, 100 of them. Not a lot of parts. But then as far as uses throughout, a vehicle, either, at home or, in motorsports, things like that, pretty much anything you'd make out of any part. Like the general limitations of additive, the size of the part is one thing that we've touched on a little bit. And, the cost, depending on what the component is, if it's, like a section of a frame rail, well, that's a big chunk of metal and it's just going to be really expensive and work the same way as your formed piece of sheet metal. So not a target for additive. But when you get into, brackets or unique pieces, unique components that, no, we need this one bracket or this one fix, this one thing that nobody else has, and we just need it to do this one specific feature. Additive's a great fit there. But then it's being used kind of everywhere. Formula One, huge user of additive. It's getting to the point now where a lot of the metal components that you can't really see, they're hidden under the body, but many of the components that are made in metal, they're making them additively just to optimize weight, just to optimize performance, load paths, things like that, because they can fine tune all of it.
Sure. I'm not sure if you're going to be able to speak to this, but I think a few years ago I was at either PRI or SEMA, and there was a additive manufacturing company had a bunch of parts on display, and one of them was a piston and another was a valve, and the valve was sort of cut open down the middle and you could kind of see the lattice structure internally. So it wasn't a solid part. Obviously, the benefit of weight saving, stuff that you couldn't make this using traditional machining techniques. And we posted these up on our Instagram and sort of got a lot of disbelief that these were actually genuinely parts that were being used internally in an engine. And I mean, I get that concern. Likewise, to sort of go a little bit further, the sort of rumours that I've never been able to see substantiated about the likes of Ferrari, I think was the F1 team that was mentioned using additive manufactured pistons in their current hybrid power units. How realistic is that? Can you give us any insight, or are the NDAs very firm in this area?
think the answer is I can neither confirm nor deny, but no, right? The material properties are there. The ability to manipulate the part after printing to get it to do what you need to do is there. Again, when you're getting down the path of, I need this one part to do exactly this from a thermal stress standpoint, a mechanical standpoint, and the ability to tune all that, the technology is there. The technology, believe it or not, is capable of doing it. Titanium, aluminum, things like that. And there's ways to process it to do exactly what you want it to do. And yeah, there's definitely truth to these parts being printed and used, highly optimized, and it can create a functional part that can stand up and perform in that environment for sure.
Yeah, okay. Good to get some kind of almost confirmation there. Now, but before we move into sort of my next question, I think we need to start just have a quick conversation about what this term means. So generative design. Can you give us a quick guide into what generative design is and why it exists?
Yeah, sure. So generative design, bunch of different terms for it, generative design, topology optimization, things like that. It's kind of the sweet spot of, part or product or component design meets the math output of an FEA, a finite element analysis. So basically, if we'll use a connecting rod as an example, there's a connection at one end, a connection at the other end, and load transferred between the two of them. Traditionally, everybody knows what a connecting rod looks like because that was the convenient shape to cast them, and it held up to the loads that it needed to transmit, and it worked great, and problem solved. If you take that connecting rod from a generative design standpoint, it can go through using that finite element analysis and basically piece by piece whittle away material that's not providing significant structure or transferring significant load. And I'm sure anybody can go on the internet and search generative design or topology optimization, and you'll see what components look like using that software and that technology. But basically most of them end up looking like some type of spider web or some type of organic shape where the math and the finite element analysis is going through and predicting exact loads on those paths, and then back calculating how much material needs to be along that load path to support that load. And anything that's not on that load path or out of the way, it doesn't put that material there. It's not needed.
Just the material it needs, where it needs it, and nowhere else. So you can make your software optimize a part for a given purpose. Maybe you want to minimize weight, which would probably be the main one. So as long as it knows what the stresses involved are, it can do exactly that. As you mentioned, we get these kind of crazy organic looking shapes. And why I wanted to talk about generative design, as I see it, it lends itself really, really well to additive manufacturing, as opposed to quite often the designs that we come up with using generative design would be difficult or more often completely impossible to machine using traditional technology. So do you sort of see generative design being a perfect fit for additive manufacturing?
Yeah, absolutely. You hit the nail on the head there. I have customers that come to me all the time and say, hey, I've got this block that's machined. Can you print it? And usually my answer is, yeah, but why would you want to? You're using additive that's not driving any additional features, functionality, performance into the part. Or when you start getting down the path of generative design, you're designing a part now that you can't manufacture any other way, and you can make it an additive. Now you're really leveraging additive to drive performance or drive, function into your part that you can't do any other way. So if you're designing a component that could be machined, but then you could print it, well, why not take it to the next level and take advantage of that generative design and make it a part that's truly optimized that you can manufacture with additive?
Yeah. All right, just like we talked about with the plastic printing, can you give us kind of an insight into the range these machines run to price-wise?
Yeah.
Just to scare everyone off.
Just to scare everybody away. Again, same thing. It's on a scale, from 3D Systems at least, we're really targeted to the industrial throughput, industrial make parts all day long in production. High usability of these machines. They're a very robust piece of equipment. So our smallest printers, which actually print fairly small parts in the grand scheme of things, I mean, you're still looking at probably $200,000, $300,000 for one of those printers. all the way up to our biggest printer with all the bells and whistles and accessories and everything else. I mean, you can be over $3 million USD, and the sky's the limit after that, because there's other systems on the market that will blow that number out of the water, and the scale anywhere in between. It's how big of a part do you want to make, and what do you want to do with it? That's really it.
Now, I'm guessing at this point, with the numbers that you've talked about, a lot of our listeners will be questioning why they're even listening to this. But the reality is that there are still options for the enthusiast market to basically leverage this technology without having to dump down a couple of $1 million. And this is through companies that will have purchased one of your machines or maybe a competitor's machine, and then will actually allow you to have your parts manufactured by them. So you're only paying for the manufacturing and obviously the metal that's used, correct?
Yeah, exactly. So the same way, if you don't have a CNC in-house, you can find a machine shop that you can send your design or your component to, and they'll machine it for you and send you back the final part. There's service bureaus out there with metal or plastic printers, for that matter, that you can send your design to, and they'll print it for you and send it back out. Same way you'd contract a machine shop to get a part made. There's plenty of service bureaus and growing rapidly, the number of companies out there that are adding additive to their portfolio. Even a lot of traditional machine shops that are heavily rooted in CNC, traditional machining, they're adding additive technology because it fits a need. It's a tool in the toolbox to create parts, and they're are accessible to the average everyday person, all the way up to the Formula One teams that use it day in and day out. You can get your hands on it for sure.
I mean, a good example, if people want to check that out as well, past guest Stefan Papadakis from Papadakis Racing, he's got a few YouTube videos which I found really, really interesting about the process of using additive manufacturing to make a bespoke one-off turbo exhaust manifold as well as an intake manifold. And Stefan does not have that hardware in-house himself, so it is accessible. I can't say it's going to be cheap even to have the parts made, but it might be a solution for a given problem. We haven't talked about this, but I assume the same goes with these support structures for additive manufacturing in metal as it is in plastic as well.
Yeah, yep. So kind of a necessary evil of holding that part, locating it in place, and getting it to print. But then obviously those supports have to come back off afterwards. So kind of a pro and con. The third piece that I mentioned earlier to metal additive is not only is it locating and holding the part in place, but the other main function of those supports is actually transferring the heat out. Metal additive, it's a welding operation. You're micro welding metal. That obviously generates a ton of heat, and if you don't get that heat transferred out of the area that you're working, the metal will physically overheat, and that causes all sorts of problems between a bad part or a failed build or things like that. So the supports are in there kind of to hold that part of it up as well.
Yep, makes sense. All right, let's move into talking about a few case studies. So we've already talked about F1, and it sounds like at least Sauber and Alpine are nice enough to actually share some of what they're doing, and there's some case studies on 3D Systems website. Sounds like probably all of the F1 teams are using the technology, but maybe not quite so open. So we already talked about the use of plastic printing for testing bodywork, and obviously that's a smart approach to testing parts rapidly. Are there any other areas in Formula One that you can talk to us about?
Yeah, high level without disclosing anything, structural components, and kind of like I mentioned earlier, anything you can point at from a metal perspective is either being printed or being considered to print. The FIM is opening up more regulations on what components can and can't be printed and what materials are allowed and approved to be printed with, and that proliferates more and more throughout the car. I believe you can see it on on our website, or you can kind of search around and find it on the internet. We did a really cool project with Alpine a few years ago that they needed a hydraulic accumulator in one of their systems. And hydraulic accumulator, any sort of accumulator, traditionally the strongest shape you can make is a ball, right? It's a sphere to hold that, accumulate that pressure change, things like that. And that's what they needed in their system, but there was physically nowhere to fit that part inside their car. The size, the amount of volume that they needed, it didn't fit anywhere at all. And guys, they're really outside the box thinker. One of the cooler parts that I've seen decided, well, what if this ball, instead of being a sphere, was just a tube? Okay, That works. How long does the tube need to be? Well, it needs to be 10, almost 12 feet long to get the amount of volume that we need. Okay, well, where are we going to put that? And they actually used metal additive to create a thin tube. It was probably quarter of an inch of diameter on the inside of the part, maybe 5 millimeters or so on the inside of the part, that was technically 12 feet long, but it was then coiled on top of itself to make a part that ended up being basically the size of a pancake. It was a disc the size of a pancake. And then to take that one step further, the whole thing got bent at a really obscure angle because they smashed it underneath a body panel nested in between three different components. And there would have been a ball that was 6 inches in diameter. And now it's this thin pancake feature nested just where they needed it to fit it in the car, and they wouldn't have been able to do it any other way.
So essentially, if you can imagine it, you could make it.
There's still limitations, but yeah, it's pretty close to that. Yeah, exactly. So one of the cooler examples, and again, we touched on this, but the amount of examples and things like this there are in the Formula One space is endless, and it's all under NDAs. It can't be shared. They don't want to, and the main driving factor of that is the rules and regulations of F1. Everything is so tight that anywhere that somebody's getting an advantage, they want to keep it under wraps because that's where they're getting their advantage from, right? But other kind of unique examples and how we kind of got connected is the work we're doing with one of our partners, BBI Autosport, which I'm sure people have heard of, shop out of Huntington Beach, California. They do a ton of work with metal additive between customer cars, builds, and things like that. But one of the main motorsport races that they do is the Pikes Peak Hill Climb in Colorado Springs every year. And Pikes Peak, and part of the reason why we're talking on this podcast is the rule book to Pikes Peak and the rule book to racing is like 3 pages long.
Yeah, got to have 4 wheels and that's about it.
And that's it. And because of that, your possibilities of how you can design a car or how you can make the performance out of it is so wide open that there isn't this like crazy amount of competitiveness of like, oh, I can't show you what I did over here because I don't want you to see it. It's super out in the open, and they want people to know what they were doing, and they want people to see it. So BBI, we're partnered with them. We work on a bunch of different projects, and there's a ton more coming between the two of us. That's really, really exciting. Pikes Peak, customer cars, things like that, where they've absolutely embrace the use of additive and where it adds value, where it adds performance, and they're happy to share it. And you can see it. You can go to their website and see examples of it, and there's going to be a lot more coming between the two companies, but they see and leverage the technology and what it's capable of doing. But then on top of that, they're also open to showing it. They're open to sharing it and have the public see it.
We've actually got a really great interview with Dimitri from BBI on our YouTube channel, so maybe we can link to that in the show notes as well if people want to dive into a little bit more around how BBI are using it. One more example I just wanted to talk about. We sort of covered this off air before we started recording, but in the Formula One realm was the use of I think it's called an eggshell mold for making silicon or polyurethane componentry. I think it might have been Sauber that were using that technology. You talk us through what that is and why you'd use it.
Yeah, so we tangented on this a little bit prior, but this is another use of additive to create not the end use part, but an intermediate step. So we use it a lot in castings where you can print an investment mold and insert to make a cast component. Then you go out and cast it. Kind of similar idea here. So we've developed a technology using some of our SLA materials and SLA technology where you can print an extremely thin and extremely lightweight mold of a component or a feature that you can then injection mold the material you actually want to make it out of. So in this case, gaskets or bushings. 2 huge benefits. One, you can print a mold and you can make a part that's completely one-off in a number of hours. 2, additive in general, I'd say one of the kind of constraints, one of the limiting factors is the materials that are available. Using this molding technique, this molding technology, you can use whatever material you would have made the gasket, the O-ring, the bushing. You can use the same material that you would have made it in the first place, but now this allows you to quickly make a unique shape, a unique gasket, a unique O-ring that you couldn't have any other way. So it's very, very thin, very, very lightweight plastic mold that intentionally is extremely brittle, that holds its shape long enough for you to injection mold silicon, for example, for a gasket. You can injection mold your whatever flavor of silicone that you want to use, let it set up, and then once the part is fully cured, set up, ready to go, you basically squeeze the entire mold. You break it like an eggshell because it's intentionally fragile. The mold disintegrates, falls apart, and you're now left with a one-off complex gasket O-ring that you wanted to make in the first place. So F1, like gaskets, O-rings that are one-off. Every component that they use is optimized from shape, size, flow, and things like that. And therefore, 90% of it, there's not gaskets that exist for this, right? And now they're getting into bushings, other components. We've actually just did a pretty interesting project that I, again, can't talk about, using this technology in a really, really unique way of something I never even would have thought of to, manage flow over a part. So lots of different uses, but basically highly complex generation of components, O-rings and bushings and things like that you can't make any other way. You can now iterate really quickly and do it kind of in real time to make these complex parts. So using additive is a manufacturing method to then get you to your end part versus just manufacturing the end part.
Yeah. I'm guessing from what you've explained with your involvement with F1 here, that these teams also aren't just buying the machine off you and then you never hear from them again. It sounds like they're maybe coming back to you and going, hey, we've got this crazy idea, we want to do X, Y, Z, and then engaging 3D systems to kind of work out how to use the product in order to achieve that outcome. Is that sort of, am I picking that up correctly?
Yeah, absolutely. It's always a combination of both. Sometimes, it's here's the printer, here's the technology, here's the materials, and they, go off and figure it out and do it all on their own. But in the terms of Formula One's, pushing the performance limits and the performance boundaries of Formula One and performance in the car itself, they're also doing that with all the technologies that manufacture their components. So we've got tight relationships with a lot of these teams because they're constantly, what's the newest, what's the fastest, what's the latest? We want to know, we want to optimize, they're in there, pushing our limits so they can push the limits of the component that they end up creating. So we do lots of development with these teams. We do lots of beta testing of machines and materials because they want to be on the absolute cutting edge of what's technically available at all times. So there's always, feedback and communication loops to facilitate that.
This is probably a good place to sort of talk about where you see the current limitations with the technology. And I guess if you can gaze into your crystal ball, this is still a relatively new field. It's developing rapidly. If you could gaze into your crystal ball and tell us what you see for this technology, what is it going to look like and what's it going to give us the potential to do in, say, 5 years' time?
Sure. The analogy we always use is bigger, faster, stronger. So parts that you can manufacture with additive will continue to get bigger printers, bigger build volumes, things like that. The material properties will continue to get better. More and more materials will be available. And then the other big piece of that we kind of tangentially mentioned is throughput, right? The speed of making a part with additive is still slower at times than traditionally manufacturing a part, and getting that productivity, getting that throughput increased, because then that makes the technology more and more usable in production-based settings where it, maybe it's limiting factors. You can't produce parts fast enough or cheap enough. Well, as that starts to iterate and performance goes up, speed of and throughput of manufacturing goes up, now it starts to become a solution where before it just couldn't compete on a speed or a cost perspective. Now it can. So those are kind of the big pieces there. And then the front end of it is the software things, where talking about FEA is getting better and better and more sophisticated and more hands off from a user standpoint, where you kind of feed it into the software, let the software do its own thing. Definitely more of that coming in the additive space as well, where we touched on it a little bit with supports, that some of it is still manual processing. It'll get to a point that it's all fully automated. I mean, I always joke that part of the reason why I'm at this company and in this industry is because I want to see what it's like 30 years from now, where you send a 3D model straight to the printer without doing anything, and your part comes out in, an hour later or something like that. Totally confident the technology will get there, especially at the rate that it's maturing and developing. And I want to be along for that, and I want to help that process happen.
If we look at, there's a bit of a tangent here, but if we look at sort of what happened in the enthusiast market with plastic 3D printers, and the rapid sort of drop in the price point of those to the point where now you can get a decent quality 3D printer for, under $1,000, for example. Obviously, the additive manufacturing using metal is a newer technology. Obviously, there's a lot more goes into that, hence the price point of the machines. Are we going to get to a point, and I don't know, maybe it's 10, maybe it's 20 years in the future, where these do get to a point where they're within reach of the enthusiast market, or are we always going to have a price barrier?
No, absolutely. I mean, it's like your plasma TV where they came out and they were $5,000 and now you can go get one for $150. The technology is accelerating at that same rate and going down that same path where making it more accessible just makes the technology more proliferated throughout the market as a manufacturing method. And it's definitely doing the same where, the more you can optimize it and the more you can make it cost effective and cheaper to do, then that technology kind of takes a bigger foothold in the market. So definitely that metal additive is kind of a unique ball of wax. It might be more on the 20-year end of things before people have it in their house, but it's definitely working that way. And even FDM deposition style printing, nobody had one of those in their house 10 years ago, and now who doesn't, basically, at this point.
Yeah, exactly. As I've said numerous times on the podcast before, if I had access to that sort of technology back when I was building my drag car, it's like the quality and finish of the parts that I could have made for it would have just brought the whole thing up another level of professionalism. So kind of almost a missed opportunity, but hey, the technology didn't exist back then, which I guess is also kind of showing my age. We'll move on. I wanted to talk about one more case study, and this one's kind of a little bit near and dear to my heart because it involves a 4G63 Mitsubishi engine and also two past guests from the podcast, which is Miles Kerr as well as Lucas English from English Racing. So as I understand, they kind of reached out and worked with 3D Systems to come up with a unique solution for an oil drive pulley on the 4G63. So a little bit of background on that is that for those who aren't aware, the oil pump on the 4G63 engine is driven off the cam belt, and that's fine and works pretty well on an engine that revs to a factory rev limit of 7,500 RPM. But in a drag racing application where we're revving more to 10 or maybe even 11,000 RPM, all of a sudden that oil pump's being driven way faster than Mitsubishi ever intended. So they wanted to design a pulley that was basically overdriven to slow down the oil pump, get it back in the sort of operating range. So what technology is sort of applicable to making something like this? How did English Racing go about doing that?
Yeah, so I mean, the whole use of additive in this case is a perfect example. It's a one-off part that's highly targeted at one specific solution and one specific solution only. So, like you mentioned, the changing of the ratio that oil pump was running at was just down to the raw design of the part, and then using printing and the materials available, you reduce weight and then make that part stronger while being lighter, reducing reciprocating mass and things like that. So it really, falls into a sweet spot of we need one of these, we need it to be extremely precise. You can't just go buy one off the shelf, so the part itself doesn't exist. And then there's benefits from rigidity and lightweighting and things like that they could do there. So this one, great example of the sweet spot of using the technology to solve one explicit problem at a low scale and be able to produce it quick, right? The part itself, I mean, normally for the most part, that type of part is aluminum and it's extruded and then welded together or some sort of stamping or powdered metal part to begin with. And to get the tooling to do that, or just to have hog one out of a piece of billet, is not quick and it's not cheap. Where this part, kind of falls into a sweet spot from a mass standpoint, where printing it versus machining it, you're almost same for same, and we could turn around and print this in an extremely short amount of time and get the part performance beyond what it would have been otherwise.
I think as well, if my memory serves correct, once they'd sort of prototyped and proven that one-off part, they obviously have a lot of 4G63 customers, and I understand they actually went through the process of using additive manufacturing to produce a production run. I mean, it was only, I think, in the range of about 35 parts, but again, at that point, additive manufacturing still much more cost-effective than traditional methods of manufacturing that scale or range of parts, correct?
Yep, exactly. That overlap between different manufacturing technologies that I mentioned, there's that still fell within that zone where ultimate total cost of those 35 pieces was still cheaper than doing it with another method just because the run was so small. And then at that scale, you start taking advantage of, well, printing one part at a time in metal additive is pretty expensive. But now when you move to 35 pieces, they probably print 9 or 12 of those in a single build. And now you're taking that whole build cost and dividing it by, call it 8 or 10, and that really starts to drive the piece price and the piece price down and the efficiency up. Where, yep, additive becomes a totally viable solution.
Yeah, makes a lot of sense. All right, Joe, we'll move towards wrapping this thing up, and we've got the same 3 questions we ask all of our guests. First of those is, what's next in the future for you and or 3D Systems?
Yeah, for sure. A little bit of both. 3D Systems, kind of like I mentioned, one of the biggest names in the additive space in general, and just bigger, faster, stronger. That's what I keep going with. More printers, more material availability, higher throughput, bigger build volumes, all that stuff. It's all in the pipeline. It's all coming, and to see this technology proliferate across industries, like I said, it was super high hold in the healthcare industry, and then it branched out to the aeromotive or aerospace industry and that kind of realm, and then branched into some other industry, and it's starting to proliferate industry to industry, which is great to see, and that will continue to spread. So more usability, more industries that we're involved in and taking advantage of the technology, and then more print platforms, bigger, faster, stronger, cheaper piece prices out of the machines. That kind of thing is kind of the name of the game. And then on my end, I mean, just trying to push the boundaries of what we can do with this technology and in the areas that I love, which is motorsports and the car industry. So working with customers such as BBI and things like that, where we can start to really proliferate what the technology can do and get it into, more of a production setting where you can call BBI up and say, hey, I've got X, Y, and Z Porsche, and then I saw you made this component. We want the same additive component, and that can be supported. So kind of driving this technology wherever I can in the autosports industry, because that's my passion. That's what I love, and I want to help out where I can.
Exciting times ahead. All right, next question. Is there any advice you'd give to a younger version of yourself to help reach where you've got to today in your career faster? Or potentially maybe avoid some pitfalls that you've come across along the way?
Sure, sure. I mean, this is probably nothing that hasn't been said before, but get out there and do it type things. You always hear stories of people, started sweeping the floor somewhere and then got their foot in the door and worked up from there. If you've got any sort of bandwidth, volunteer, things like that. There's a shop nearby that's building drag cars, for example, and you want to get involved in it, go tell them you want to sweep the floor. Go tell them you want to, turn wrenches on the weekend type thing. Any bandwidth that you can dedicate towards trying to do that, you'd be surprised on how many people are willing to say, yeah, we could use the help or things like that, or how much a simple conversation of, hey, I'd love to help out with that. Oh, cool, we could use some help, right? Just putting yourself out there and trying to have those conversations. I wasn't a talkative kid when I was younger, and I wouldn't have gone down that path. But had I known, all I had to do was speak up and say, hey, I want to help, and I'm not even asking anything to come and help, that would have opened a lot of doors even sooner than it already did. So get out there. The community, from the car perspective in general, everybody wants to help out. Everybody likes to be involved, and just go put your name in the hat and try to get out there and help where you can. And that opens more doors than anything else, in my opinion.
Yeah, I think that's great advice. Absolutely, couldn't agree more. All right, last question for today. Joe, if people want to follow you and see what you're up to, how are they best to do so? Social media accounts, websites, etc.?
Yeah, so from the 3D System side, all the social media, search 3D Systems anywhere else you'd like. From my side on the LinkedIn and things like that, I'm not huge in the social media space, unfortunately, for better or worse, but definitely go see what 3D Systems is doing. You'll see some of the work we're doing and my name out there on some of the projects that we're working on. And as more and more of that comes to the public market, and keep an eye on that, and really look at additive as a whole industry and what it's capable of doing. You'd be surprised that it might be a little bit more accessible than you think, and where you can utilize the technology to do some cool things, and it's worth keeping an eye on.
Ideal. Well, as usual, we'll put links to the accounts in the show notes to make it easier for people to find. But look, Joe, I mean, it's been an absolute eye-opener for me. I mean, I was sort of on the fringe of my knowledge with additive manufacturing as it was, so great to actually be able to dive deep into it and get a bit more insight into where it's being applied and maybe what the future holds. I mean, certainly outside of the automotive industry as well, what you were saying about, producing organs, I mean, that is absolutely mind-blowing and will definitely be an absolute game changer if and when that comes to fruition. So exciting times ahead. Really love talking about new technologies and seeing all of the applications, these smart people who are able to push the boundaries and then use this technology to the extreme, what they're actually doing. So thank you very much for your time. It's been really, really interesting chatting.
Yeah, absolutely. Thanks for having me on. Had a blast.
If you enjoyed this episode of Tune In with Joe from 3D Systems, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Corey Welsh from Canada, who has said, "Love the content. As a VIP member, I use the podcast to get me between modules and or courses. I am listening in order. Very cool, very interesting, and very informative." Well, Corey, great to hear that you are enjoying the podcast episodes. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.